All right, so the next goodness of fit test we're going to talk about is called the chi-squared goodness of fit test. And I'm going to set it up for you all just kind of conceptually. It's very similar to the QQ plot, but it's an actual statistical test that we can do where we get a p-value, we get a test statistic, and this is really our first formal introduction to test statistics and p-values. We're going to cover it more rigorously next week. What we're doing here is we're comparing, very similar to the QQ plot, but comparing observed frequencies of observations. We're kind of binning the data, so we're going to a histogram. The observed frequencies to expected or theoretical frequencies. From a particular distribution. And this can be any distribution. We'll start with the normal, but in the data analysis project, you guys will actually look at different distributions. So say we have n observations. In a sample. And we want to see how well the normal distribution fits. Fit the data. Did the data come from an underlying normal distribution? Of course, we can do our QQ plots, we can do our histograms. Those are all really good visual types of exercises, and that's really important. But we can also do a statistical test here. So what the chi-squared test does is we break our sample up into k bins and calculate the frequency of observations. In each bin. So these bins are going to be equal width. So the frequency of observations we'll call O sub I in each bin, which would be K sub I. And then we'll compare these. Observed frequencies with expected frequencies or probabilities, right? From a normal distribution that we split up the same way. And so what this looks like is here's x, here's f of x, and we'll do a histogram of our values. We'll fit that normal distribution with the same mean and standard deviation as our sample. It's going to be a little bit different, right? And so in this case, we have 1, 2, 3, 4, 5, 6 bins. So k is equal to 6 bins. And then we have all of our observations, observed frequencies, right? And then under each of these bins, we also have these areas, right? So this is going to be E3, E4, and that's going to be the area under the curve within each bin range. So once we do that, then we can calculate this chi-squared metric. We're going to call it the goodness of fit metric. So this is the chi-squared metric. So there's chi-squared, and that's equal to the sum from I is equal to 1 to k of our observed frequencies minus our expected frequencies or probabilities squared all over our expected. It's a very simple metric. How far off are observed frequencies from our expected, dividing by each expected one. And we'll note that, and this is just kind of some underlying probability theory, that this chi-squared metric follows a chi-squared distribution as n approaches infinity. So as n increases in value, we get this. And then there's one other parameter. So the chi-squared distribution has a parameter, which is just our degrees of freedom. So when we plot the chi-squared distribution, we need to know what that is. And just make sure I know what that is. Okay. So our degrees of freedom, df, is equal to k minus 1 minus the number of distribution parameters. And we'll say this is the test distribution. So for a normal distribution, this is equal to 2 parameters, the mean and standard deviation. And that's usually what we're doing. But you could say, I want to see if my data fit an exponential distribution. How many parameters does the exponential distribution have? Just 1. So this would be k minus 1 minus 1. Okay, so the last part of this, and hopefully I can wrap up in 2 minutes here, is once you calculate that chi-squared statistic, we can test. This is our statistical test. Whether the distribution of our data is significantly different from, in this case, the normal distribution, but it could be any distribution. And the way we test this is we calculate the probability of observing the chi-squared value or chi-squared metric, just like a z-score. And so there are chi-square tables. The idea is if we have this chi-square distribution, which kind of looks like this, it's a skewed distribution. then and we calculate our test metric. So we do that and we get this chi-squared value from our sample based on the normal distribution. We say, what's the probability under this curve or up to that point? And so we just set that value, and that could be, it's just an arbitrary value. So it could be, and typically this is the area under the curve should be 0.05, and this is 0.95. And if our score is high enough and we calculate the probability up to that point, and it exceeds this threshold, then we can say it is significantly different. And so I'm just going to set this up real quick. This is, well, first we'll do this. We'll say our null hypothesis. So null hypothesis, H naught, is that the distribution of observations is different from the normal distribution. And then our alternative hypothesis, HA, is that the distribution follows a normal distribution. Oh, sorry, I set that up incorrectly. This is going to be our alternative, and this is going to be our null. So null and alternative. So do we accept the null hypothesis or do we reject it? And so the question is, can we reject H naught, our null hypothesis? And so in order to do that, we calculate our chi-squared metric. We see what the probability is up to that point. And if this is in this region, we cannot reject H naught, and in this region, we reject H naught. And we say that it in fact follows a normal, oh yeah, it in fact does not follow a normal distribution. So if we see a really extreme chi-squared value, that means our values diverge from the normal distribution. The expected values diverge from a normal distribution. And so if you're in this region, then say it's over here, then we say, nope, it's not different from a normal distribution. So we cannot reject the null hypothesis. And in fact, it does follow a normal distribution. So over here, the distribution of observations is different. And here, the distribution is the same. And ultimately, we just want to test that. Does it follow normal distribution or not? Can we reject it? And then if we do reject it, if we do get this extreme chi-squared value over here, then we will simply say, okay, let's try another distribution, see if it fits that. Okay. So we'll in class next time actually go through the mechanisms of how to do this, and we'll run some code in R. Please bring your computers. And so we'll see you next time.